All right, good morning. Welcome to the start of week 8. Today is Wednesday. There was no Monday. A couple of announcements. The final project spec is out and on the course's website and also in your hands. Notice that this has several deadlines per the syllabus, which will pretty much take us through the end of the semester. If you have any questions, let us know. But the first such deadline is about in 2 weeks after Thanksgiving break, the idea of which is to pre-propose one or more ideas just to get the juices flowing and to get some feedback from your teaching fellow. If you have any questions, though, in the meantime, do ask us. Quiz 1 will be returned at the end of lecture, so do see one or more of the TFs who will be stationed outside that door and outside that door, and they'll announce right at the end of the class where to go and whom to get your stuff from. Any questions about stuff? No? All right. Well, recall for problem set 4, the group of you were tasked with finding a whole bunch of photos. We thought we would reveal the efforts of one such section. It was fascinating and wonderful to see how many of you got into this. In the end, the competition came down to a few different sections, one of whom ultimately triumphed, whom we'll formally announce in a moment. But of course, there were 38 different photos in here. What's striking, I think, about this photo, and I myself did not take this makes this room look absolutely beautiful. And yet, when you're here, it doesn't quite feel like that utopia, much like that Science Center photo. But this, in fact, was found. If you haven't noticed this guy here is in Harvard Square, so right across from the Coop. Can you find that one? That's been there as long as I remember. There were a few that were kind of fun or kind of hard to find. Emerson wasn't so hard, probably. So these guys here, Lauren went so far as to not only photograph herself in the fish, but also to say the fish we care about is on the left. So they identified the fish down to the fish, which is pretty damn remarkable. So that was over at the business school, which actually is a wonderful utopia to escape to. This little, not the school, but the chapel that's over there has this indoor aquarium, essentially, which is absolutely wonderful to hang out. These guys, too, found one of the many ass stances on campus. This, too, has been here as long as I can remember, and it continues to fascinate me how they don't just write help or anything other than assistance. It seems they've never yet learned. Since it's such an easy joke to make. A few others. So this one's kind of cute. This too is in the square, right across from the Coop. Dewey, Cheatham, and Howe. I think this has actually been featured. This has been a gag for many years, but it's supposed to be a law firm. But if you pronounce it slowly in your head, you'll see wherein lies the humor there. What else we got here? There you go. All right, a few signs on campus. I was actually surprised how many folks got this one wrong. So this is Mather Tower looking straight up. So these guys did in fact find this. We got one of the houses there. What else? The Science Center mirror, of course, pretty straightforward. This one's kind of faded over the years, but what was cute about this one, and you can kind of still see it, some hooligans put a T on the letter T on this sign for a while, which is kind of funny because Harvard Square is to the right and not Harvard is to the left. So unfortunately, someone pulled that off over the years. What else was tough? Actually, there was one that I was quite impressed that these folks and a few others found. So this symbol here, frankly, I'd never seen it until we started sniffing around for interesting locations, is a deer-like symbol on the back of the John Harvard statue. So these guys actually did find that on the very back of the statue. So nicely done to them as well. And finally, what else we got here? Down there. So okay, so this, of course, you hopefully get the gag. This was just a screenshot I took of the DVD. And these guys, too, apparently own the DVD and were able to find it as well. So I think they get bonus points for that. And then the last, of course, was Malin Rouge, which is a sign a friend of mine made up on my old grad student office. So these guys, too, found this outside Maxwell Dworkin 309. So a big round of applause, if we could, to Chris and these guys here, his section. Is Chris himself here? Yes? No? OK, well, representatives from Chris's section, if you'd like to come down. Lauren, is she here? Anyone else from Chris's section? Chris Stevens' section. Is there anyone? All right. Mind you, these are the guys who we're sending to dinner. So Andrew, on behalf of Chris Stevens' section, we award you this. And if you don't mind one moment of awkwardness, we also got you guys this, which you can decide what to do with. But perhaps one of you can hang this in your dorm room. So the prize for finding the most photos. So congratulations. A big round of applause for Chris Stevens' section. We did want to acknowledge at least 2 other students, both of whom submitted a ridiculous number of photos, and frankly, I think without the support of their section, since they were in absolutely every one of these photos. But Patrick Quinn and Chris Olin, we'd like to invite you to dinner with Chris Stevens' section if you'd like to come on down and get your certificates here as well. So it's perhaps fitting that these 2 guys are here, given how much they put into this. Another round of applause, if we could. All right, congratulations. All right, so as for the hacker dinners out, we will announce that via email to the folks of you who submitted the hacker edition of that problem set. All right, so without further ado, this week's goals are twofold. One, to introduce you to another real-world application. That is compression, since it will be the focus of problem set 6. And nicely enough, the implementation of this concept of compressing data will allow you to apply some of the stuff we've been talking about of late. Trees, possibly heaps, linked lists. So this will really bring the course to a nice end so far as our focus on C is concerned. What we'll do on Friday is take a look under the proverbial hood and finally take a step back and ask ourselves, when you run GCC and actually take something like hello.c and produce hello or a.out, what really is going on underneath the hood? Assembly language, what is that all about? Ant8, which has been on the syllabus for quite some time, we'll essentially take a look at some lower level details just to make you a bit more familiar with what you've really been doing by typing these commands at a higher level this semester. So that will come on Friday. And on Monday, we'll have our secure coding lecture in which we'll finally dabble in more concrete details as to what it means to write secure or insecure software and how all these bad guys in the world are taking over things like the iPhone by way of buffer overflows and the like. So here's something you might remember. Most of you probably haven't memorized these codes, but presumably you all know what Morse code is. It was a mechanism for transmitting signals, typically by way of, say, electrical pulses or beeps, so that you could send a message across a wire, used by the military and others. So what's the motivation for something like Morse code, do you think? Right? Why was this used or invented in the first place, would you hypothesize? Yeah.
The ability to broadcast an on or off signal.
OK, so if really the only form of communication you have electronically is this ability to send a signal or not send a signal, well, you have to sort of quantize the information you want to send. And using something like a dot, which just means holding the button for a moment, versus a dash, which means holding it for multiple moments, is one way that you could map letters of the alphabet or entire words to a nice encoding scheme. So this is sort of similar in spirit to what we try to do when we represent letters of the alphabet with computers in the first place, right? Quick review. What's the whole coding system we use to represent characters using numbers? That's right, so that's just ASCII. But with ASCII, how many bits are we spending to represent an individual character? So 8, right? An ASCII character is 8 bits. It's the size of a char, so 8 bits. So that's fine, and it makes for a nice deterministic system, right? It always works, it seems. But the problem is, perhaps, that you're wasting bits. For instance, what number represents the capital letter A? All right, so 65. And how many bits did we need to represent the number 65? So we have the 1's place, the 2's place, the 4's, the 8's, the 16's, the 32's, the 64. So we only needed 7 bits total to represent a capital A. And in fact, if most of our messages don't need weird punctuation symbols, but just need alphabetical characters, maybe an apostrophe, similar in spirit to the speller program, you can probably get away with even fewer bits, right? If you only, to simplify, have to represent 27 different characters, much like you guys are doing for speller, maximally how many bits must you have to express words from a 27-letter alphabet? How many bits do you need to represent any of 27 different possible characters? So I heard 5, 4. So we've got the 1's place, the 2's place, the 4's, the 8's, the 16's. So if we have 5 different bits, how many different numbers can we represent? 32 possible, which is good. We don't need all of those bits, right? We've got a few left over. But with 5 bits, you can represent 32 different values. So clearly, you could represent A through Z and an apostrophe. And then you just throw away some of those extra encodings. They're meaningless. Maybe they represent white space. So you only need, it seems, 5 bits to represent the English alphabet. But let's push a little harder. There are certainly letters of the alphabet that are more common than others, right? You've all probably seen Wheel of Fortune. It's no coincidence that people tend to guess the same letters early on in that game show because they're trying to maximize the odds that that letter's in a word on the board. So if that's the case, it seems almost foolish if for the most common words we use 5 bits, for most common letters we use, say, 5 bits, or worse, 8 bits in the ASCII system. And even for less common characters like Q and Z, we're also spending 8 bits. Right? Intuitively, what might be better? Right? If this problem ultimately at hand involves common cases and uncommon cases, and the goal is to be efficient, what does that sort of suggest intuitively would be nice for us to do?
You would have to use the most common.
Yeah, so use the fewest number of bits for the most common words, which means in computer science speak, optimize the common case, right? Spend as few bits as possible for the most common operations. And then even if once in a while someone types zoo and therefore needs to encode a z, fine, we'll spend 8 bits or 5 bits in that instance. But generally, we won't need to spend as many bits. So we present Morse code here as sort of a step toward this idea of encoding characters, letters of the alphabet, using efficient encodings. For instance, this chart suggests that one of the most common letters in the English alphabet is clearly what? E, right? And that's consistent with Wheel of Fortune, you would think, right? So it's one of the first valuables someone buys. So the dot means that to send an E across the wire using Morse code, you just hit a button very briefly. It's the shortest of all of the possible codes. And you can take a look at some of the other short ones. I is pretty common, and thus it is among the shorter codes. T is apparently pretty common, and thus it's among the shorter codes, even though it's a dash. That is like a 2-second beep instead of a 1-second beep, and so forth. But by contrast, Z is pretty darn long. Dash, dash, dot, dot. I mean, that's much longer than just transmitting an E. But there's a problem with Morse code, at least so far as it concerns an implementation with a computer of this idea. There's this ambiguity. Suppose that you see, let's say, suppose that you see dot dash across the wire. And you're the guy listening to these beeps on the other end. What letter or letters have you just received? OK, good. So AT or rather ET or just A. Right? And that's unfortunate because now there's this ambiguity. And maybe you could figure it out. But one of the goals of Morse code was to have these guys very rapidly translate these codes. Right? You don't want to have to go back and sort of infer, oh, he must have meant this letter here, not this one, because it doesn't make sense otherwise. You want it to just be able to stream this data across the wire and just translate things dot for dash, all at once without ever looking back. So what's an obvious solution to that ambiguity? If you're sending a message across the wire and you want to avoid the guy on the other end maybe misinterpreting whether it's a dash, a dot dash or a dot dash. Yeah, exactly. I mean, I kind of had to do it verbally there myself. I had to pause in between if I wanted to demark some kind of gap between these characters. Unfortunately, that gap itself is like sending another piece of information. And it slows down the whole process. So at least the parallel here is that we're slowing down that process. It's not as efficient as it might be because we're bumping into this ambiguity. Much better would be a system that's immediately decodable, so to speak. There's not this ambiguity, and you can just read it bit for bit, or dot for dash, and so forth, and immediately know what it is you're looking at, and not have to pause, insert these artificial delays, or effectively spend more bits. And Huffman coding in computer science is a canonical example of exactly that. So the goal of Huffman coding, as it's called, which was invented by a man named Huffman, is to compress information on disk using as few bits as possible to represent each character. And intuitively, as we sort of alluded to a moment ago, the most common characters in the body of text you're compressing are going to be encoded with the fewest bits, and the least common characters with the most bits. So what this suggests is that if you compress some text file, maybe the King James Bible that we gave you for problem set 4, or the Austin Power script, and you compress that on disk, the bits that are going to be stored on disk are no longer ASCII characters. Rather, they're Huffman characters, if you will, Huffman codes, if you will. And you can only actually look at that file as a human once you've decompressed that file, which means reversing the process and converting the sequence of fewer zeros and ones to 8 zeros and or 1s, and converting it back to chars. So this is the algorithm, but rather than dwell on the pseudocode, I think it's easier to understand if we take a look at an example. So consider this. It's a completely arbitrary body of text, but clearly there's a lot of redundancy in this file. So consider that big string in quotes to be the contents of some file. And the only reason I chose this silly example with A through E's is because it takes way too long to discuss A through Z's. So here we go. The goal is to compress this file on disk. Now just estimate. How many bytes would this file be on disk as is? You can just estimate with no sense counting up all these letters. 20? 100? Yeah, so maybe like 100 bytes, maybe 200 bytes if we counted all the individual letters, right? Each letter is an ASCII character, so that's 8 bits or 1 byte. Count them all up, that's the size of this file on disk, right? And just to validate this, incidentally, if you've never looked closely, if I am in, open up Nano and write a file called foo.txt, and now let's see, Nano doesn't like empty files. So if I put in the number 1, so I've literally added 1 character, I'm going to save this and type ls-l, which is a command you've seen before. Notice that foo.txt is exactly 2 characters. Now that's a little weird, but this is a Nano thing. And Nano has this tendency of adding a line break at the end of your file. But the takeaway is that that file is 2 bytes, one of which is the number 1 I typed, and the other of which is the new line character that Nano inserted for me. So with that said, let's assume this is 100, maybe 200 bytes total. And I, in advance of lecture, went ahead and counted up the number of A's, B's, C's, D's, and E's, and then divided each of those values by the total so that I could get the relative frequencies of each of these characters. And consistent with what you might expect in a body of English literature, the letter E appears to be the most common letter here, followed by A, which is 20% of the time in terms of frequency, 15% for D, and then B and C both appear 10% of the time. All right, so who cares? What can we do with this? Well, the way that Huffman coding works is as follows. And again, to set the stage here, the goal of this problem is to figure out what bit sequences, 0s and 1s, should we use to represent each of these characters instead of what ASCII tells us. So in other words, let's not represent A necessarily as 65 with 8 bits, but let's use fewer bits if possible. So let's see where this gets us. So Huffman coding tells you to do as follows. Create a single node tree for each of the letters of your input, and store in each of those nodes the relative frequency of those characters. So here I effectively have 5 trees, even though they're silly looking trees because they have no children, but they're roots. 5 roots of trees here. And the relative frequencies are there. And just for sanity and for nice pictorial reasons, I've sorted things from smallest to highest. But that isn't necessarily a requirement of the algorithm. This is just a visualization. So Huffman now tells you, in order to figure out what bit sequences to represent A, B, C, D, E with, go ahead and connect as children the 2 smallest nodes and create a new parent for them whose frequency is the summation of those 2 children. So with that said, the 2 smallest nodes are obviously B and C at 10% each. So Huffman's algorithm says create a new node, attach those 2 smallest nodes as children, and put what value in that new node? 0.2. All right, just add them up is what we said. All right, so pictorially what we're going to see is something like that. Okay? And now arbitrarily, but consistently, we're henceforth going to assume that the edge going from a parent to a left child represents a 0. And the edge going from a parent to a right child represents a 1. And you can flip them, that's fine, but you have to be consistent throughout the tree. So we'll go 0 and 1. All right, so now this algorithm repeats. I mean, that's it to the Huffman algorithm. Right now we just recursively apply the same idea. But looking now at the roots of all of these trees. So now we only have 4 roots, that is 4 trees. The 2 smallest ones are obviously what? What are the 2 smallest roots? So 15% and a 20%. So there's 2 different options here. I'll just keep going with the one I created, and we'll come back to this if need be. But let's go ahead and connect now the 20% and the 15%, creating a new parent whose sum is obviously 35%, 20 plus 15. So that's it. So now the next step, who do we attach to each other? All right, so 35 and the 20%. So those guys get a new parent. And again, we're still labeling the edges 0 and 1 consistently. And now the algorithm's just about done. We unite the 2 final ones. And because of the additive approach we're taking, everything should total, obviously, to 100%. Because we're just adding all of the individual frequencies ultimately. And now we have this tree. So this is a so-called Huffman encoding tree. And what this tells us now is what bit sequences we should use to represent each of these characters. In other words, henceforth, if I want to take an input file like austinpowers.txt and compress it into something smaller, rather than using the ASCII code that we've been taught to use, like 65 for capital A, 65 for capital B, all using 8 bits total, instead write out bit sequences like these, such that A is now going to be the following. Start at the root and search for A. So if I'm at the root node, I follow a 0, I follow a 1, and then I'm at the letter A. So what that suggests is that the bit sequence that will henceforth represent A in the compressed file is going to be 01. What about B? Your turn. All right, so 4 zeros. So B is 0. So let's say 1, 2, 3, 4. Yep, 1, 2, 3, 4. What about C? C is 0, 0, 0, 1. All right, and D is what? 0, 0, 1. And E, finally, is what? 1. All right, so that's sort of a nice effect here, right? The most common letter in the input text, which was 45% of those things were E's, it's clearly using the smallest of all of these given bit sequences. And again, intuitively, B and C, which were pretty uncommon, only 10% of the time each, we spend the most bits on them. So again, just intuitively, if you're optimizing the common case and spending more only in the uncommon cases, just intuitively you would think that that would actually give us an optimum result. And in fact, that's true. You can mathematically show that this is, in fact, a means by which you can minimize the total number of bits you need to use for a given input text. Now, who cares once we get to this point? Well, what exactly are we going to be doing? So if we've written a program called compress, well, compress is going to open a file like austinpowers.txt. It's going to iterate over all the characters, maybe using an array of integers so it counts up all of the total number of letters in that file. And then that program called compress makes a table in memory, an array like this. Or rather, maybe not ints, but floats. So we have frequencies like this. Then what this program compress needs to do is build somehow a tree that looks like this in memory. And then once it's done that, it needs to essentially search the tree once for each letter of the alphabet and figure out what encodings to use. And now what the program essentially has in its memory is an alternative scheme to ASCII. So long as you're storing this with some kind of array, maybe as strings, maybe as some other means, now we have the means of outputting austinpowers.txt using our scheme instead of ASCII. So to do so, we might do the following. So here is, well, rather, let's actually do this. So if this is our scheme, and we want to now output the word bad, because bad happens to be one of the words in austinpowers.txt, instead of outputting the number 66, followed by the number 65, followed by the equivalent for D, what do we instead output if we're Huffman coding this file for bad? 1, 2, 3, 4 for B. A is a 0, 1. And D is a 0, 0, 1. Which is to say, if the whole contents of the file we're trying to compress are just B, A, D in the input text, the output text, or the output file rather, will contain this. Now this looks longer, but that's because I'm writing it as zeros and ones, right? But how many bytes is this input text? So this is 3 bytes total, right, or 24 bits. How many bytes is this thing? Yeah, so it's less than 2 bytes. Specifically, it's 1, 2, 3, 4, 5, 6, 7, 8, 9 bits. So notice this is 9 bits over here. This is 24 bits. So the savings are quite obvious, at least on first glance. But there is a catch here. It's a good question.
Is it not as efficient if the frequencies between the least common and the most common are not that much?
Is it not?
If it's not that much different between seeing a Z and an A, is it still that efficient? Because it seems like we're going to have to use a lot of bits for, say, the least frequent out of 26.
So it's a good question. So to summarize, if the relative frequencies of all of the carriers are pretty much equivalent, do you gain anything or do you gain much? Short answer is it depends. Possible answer is no, you don't gain anything. For the following reasons. Consider the following scenarios. If for some crazy reason your input text has all possible ASCII characters, so crazy amounts of punctuation and letters and numbers and so forth, well then this really doesn't gain you anything, because intuitively if you have to represent all possible ASCII characters in your input text, all of which are pretty common, you need to spend 8 bits for each of them. What Huffman exploits is the reality that a lot of files don't use all 256 possible ASCII codes, but only use 26 of them, or maybe 52 of them, plus a few more for punctuation. Certainly not 256. So in this scenario you propose, absolutely, this could be a complete waste of time if you have bad inputs. But arguably for common inputs, for normal inputs, you actually do tend to get savings. But not in this case. There's a catch with what we just described. If this is the output file, and this is the input file, it clearly looks here that the output file is quite small. But is that all we need to store in a file? Yeah, so you need to save something. You need to save this information, or conceptually you need to save that information, the tree itself, right? Otherwise, if you open this file on disk, how are you, the program called decompress, going to know what each of these zeros and 1 represents? All right, so that's the potential trade-off here. For small files, what's the implication for Huffman coding? This being a particularly small file with just 3 characters. So it's not going to compress very well. In fact, what could be the crazy outcome if you compress with Huffman coding a very small file? It could actually be bigger, because you have to store metadata in the file, namely the encoding table or somehow the original tree, so that the guy whose job it is to decompress that file knows what he's even looking at. Yeah?
How large are the files do you generally have to get in order for this to start paying back to you?
Oh, good question. So where's the equilibrium point? Probably just the order of 100 bytes or 2. Right, a few hundred bytes, because really to represent a table like this, you can actually just output an array of size 256 and just store all of the frequencies that you found, even if a lot of them are zeros. So that means that technically the output file here might be 9 bits plus 256 to represent not just this, but a whole table for all possible ASCII characters. So once you exceed a few hundred bytes, which is quite reasonable, rarely have you written yourselves text files that are only 300 characters long, do you start to get some savings. In fact, and this is a bit of a white lie because this program doesn't actually use Huffman coding, but if we go into, let's say, PS5, let's see, I'm going to have to copy from CS50, pub, PS, distributions, PS5, texts. So I'm going to grab one of our texts, and if we do ls-l, you'll see the various sizes of these files, and Tolstoy is the biggest one at 3.1 megabytes. If I Oh, is it really? 4.3, even better. So let's go with this one. So if I go ahead and use a program called zip, which most of you are familiar with, and run kingjames.txt, it deflated that file, so to speak, 69%, which means if I do an ls-l and now look, notice that that same file is almost a third of its original size. Now, I say that's a bit of a white lie because zip does not use Huffman coding per se. There are other more sophisticated techniques. But what you'll be writing for problem set 5 is a program called Huff that if you do run it on kjv.txt, it will output a compressed version, a huffed file, so to speak. And you'll also be writing a program called Puff, which reverses that process and decompresses the file. Yes, it's a 15-year gag in this course. So back to this example, though. We just encoded a string. What does this string decode to, given the lessons we just learned? What does this decode to? So 0, 1, 0, 1, 0, 1, 1, 0, 1, 0. All right, so what's the first thing? That's an A. Another A. Then what? OK, another A. Then E. 0, yeah. But there seems to be a problem here. But in fact, I'll argue that this encoding is actually a compressed version of a word, or rather a compressed version using the same frequencies that we gave before. In other words, this is a valid encoding given these frequencies. So what might be the problem?
Where to start here? Like you could
Where to start reading the bits?
Start reading the bits, but part of it is metadata.
OK, so that's fair. If there's some header in this file, like you might need to yourselves embed in your with your Huff program, like the frequency count, maybe we're starting to read the bits at the wrong point. And perhaps this is too subtle. I'll actually point out what the actual problem is in this scenario. Recall this step here. So at this point in the story, we reached a decision point. What was it? Yeah, so there's this ambiguity now. There's two 20%, and the algorithm says just choose the two smallest. Well, what do we do in the event of a tie? Unfortunately, it's not clear, right? It turns out we could build another tree by connecting A and D, which would give us a new node of size 35%, and then whom would we connect? That 35 and a 20, and then we would create a new node. So that would create a different tree, and thus different encodings. But it turns out, because of the optimality of Huffman coding, that's OK. You get a different set of encodings, but mathematically, if you sort of do all the math and multiply the frequency of each character by the length of its encoding and sum all of that up, you'll still get the same expected length for each of your encodings, or each of the encodings of your file. But the catch is that you, the programmer, need to remember which approach you took. So it's fine if you store something like this in the so-called huffed file, the compressed file, because this explicitly tells you what encodings were used. If instead you take a more generalized approach and somehow store the tree or just store the frequencies themselves, your decompression program needs to reconstruct that tree. And if it takes the other fork in the road and builds a different tree, that's problematic. And what happens is then you run into these ambiguities because the developer has not actually implemented the program properly. They've not actually kept enough information around. All right, so that's it for Huffman coding. And even though we dwelled on this for a few minutes, realize that the algorithm just boils down to take the two smallest nodes, combine them, repeat. And then you get that tree. And you get your encodings, and you have a way of compressing data like BAD into something that uses far fewer bits. Any questions? Well, it's kind of neat, right? And this certainly draws in some of the ideas we've talked about thus far. Well, how to implement this in C? Well, fortunately, we'll leave that to you in problem set 6. But perhaps an obvious way or non-obvious way of representing the nodes in this tree might be something like this, right? If the goal is to store in each node not only a left child and a right child pointer, but also the relative frequency, this could suffice as the C definition for a node in a tree. And notice that even though in problem set 5 you guys are focusing mostly on hash tables and thus linked lists most likely, unless you're doing fancy things with arrays and tries, this kind of code you'll write for problem set 6 is very similar in spirit to problem set 5. But instead of having just next pointers, you essentially have two next pointers, left to right, with which to build out these trees. But more on that in the problem set and sections to come. But we need some new tricks. If we're going to start writing out things like bits to files, we need to know a little something about, ideally, so-called bitwise operators, which are perhaps the last syntactic feature of C that we'll introduce. And these are simply operators, similar in spirit to plus, minus, division, and multiplication, and so forth, but that operate on data bitwise. That is, bit by bit by bit, rather than necessarily in the aggregate, like plus does. So if you want to take two, say, bytes and their 8 bits together, you can actually use the AND operator. Notice this is different from the other thing we've seen, which is this thing, the AND. This is the Boolean AND. Just one of those things is the so-called bitwise AND. And we'll see this in context in just a moment. If you want to OR bits together, you use the one vertical bar. If you want to do something called exclusive OR, which we'll come back to in a moment, you use that caret symbol. If you want to take the ones complement, that is, flip all of the bits, zeros become ones and ones become zeros, you can use the tilde. And if you want to shift the bits over one or more places, you can use the left shift operator. Or if you want to shift the bits the other way, you can use the right shift operator. And we'll see some of these in action right now. So let's couple definitions first. If you AND 2 bits together, that means that both of them have to be true for the answer to be true. That is to say, 1 and 1 equals what, according to that logic? 1. But 1 and 0 equals 0. And as a fun in-chair exercise, go ahead and complete the rest of the top left. Oh, you don't have the chart, so I'll do it for you. We'll hand this out on Friday, this data. So if this is the AND operator, 0, 1, 0, 1. So 0 and 0, 0, 0 and 1, 1 and 0, 1 and 1. So this is a so-called truth table for the AND operator. And you'll see something like this in a hardware course if you proceed onward in computer science with more sophisticated applications. The OR operator now works like this. So same chart. So I've got a row and column of zeros and a row and column of ones. 0 or 0 yields 0. It's the same idea as true or false here. So 0 or 1, 0 or 1, 1 or 1. Well, that's an easy one. All right, and now it gets a little more interesting. We'll do the easy one first. 1's complement just means to flip bits. So if you have a 0, it becomes a 1. And this is a 1 becomes a 0. And now the one that's somewhat interesting, and this actually has really cool applications in crypto and in other contexts, that of the exclusive OR operator. So if instead here we use the caret symbol, which is XOR, and label the chart the same, the final table here says this. If you XOR one bit with another, the answer is true only if exactly one of those bits is a 1. So it's exclusive OR in that there's this exclusivity. Only one of the guys can be 1s. So with that definition, 0 XOR 0. So that's 0 because only one of them can be 1, but neither of them is a 1 in this case. What about 1 XOR 0? Right? And 0 XOR 1, equivalent formulation. 1 XOR 1. 0. OK, so that's the only one that might be a bit new, but it's actually quite powerful. And though we won't use it terribly much, there are some neat tricks you can use with it. But hopefully the ands, the ors, and the complements are pretty straightforward. So let's ask a question now. Who cares? What can we do with some of these new tricks? And they'll certainly be germane to problem set 6 when you need to read and write individual bits. But what if we take a look at binary.c, which some of your classmates did for the hacker edition of problem set 1. One of the problems on that problem set was take an integer from the user and print it out in binary. And some of you guys use tricks with arrays, but it turns out one of the simplest solutions, even though there looks like there's more code here than there actually needs to be. You can write this program in one line, essentially. You can use bitwise operators to print out each of the bits in an integer. Well, how is this going to work? Well, first of all, the top of that code here uses a do while in a typical fashion just to get an int n from the user. And this loop, using this new left shift operator and this AND operator, has the effect of printing out one by one each of the 32 bits in the value n. Well, how does this work? Well, let's take one example here. If we have a binary number, or rather a decimal number like 3 in decimal, this equals what in binary? Yeah, so, well, don't call it 11, 1, 1, right? All right, so, and then there's 29 zeros to the left of that. OK, so that's the number 3 represented in binary with an int. That is 32 bits. How does this program go about printing out each of those bits using just ASCII characters, chars? Well, let's take a look. So we have this for loop, and it looks like I'm initializing I to equal what exactly? What am I doing here? What size of int times 8 minus 1? So if you got this wrong on the quiz, recall it's in the solution key. So size of int is just 4 times 8, so that's 32 minus 1. So 31 is what I is being initialized to. The idea here is that what we're going to try to do is print out the integer from the 31st bit to the 30th bit, dot, 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 to the 0th bit. So that's the goal of this loop, to literally iterate over the bits of the number. So we're going to do this while I is greater than or equal to 0, and we're going to keep decrementing on each iteration. Now here's an interesting line. OK, so we're defining what's generally called a mask, which is just a sequence of bits that we're going to use to our advantage. That's the result of taking the number 1 and using left shift I. Now, I promised before that the left shift operator takes the bits in a number and shifts them literally to the left, or to you, to the left. OK, and if that means clearly you're going to have blank spaces on the right-hand side, those get filled with zeros. OK, so what do we mean by this? Well, if we do 1 left shift 31, what does that mean? Well, what's the number 1 in binary? All right, so it's a whole bunch of zeros ending in a 1. All right, so 31 zeros followed by 1. So this is old school stuff. All right, now the left shift operator is saying shift those bits 31 places. So what that literally means is every bit in this array, or rather in this sequence, gets moved 31 bits to the left. So what does that have the effect of doing? Here's the int. So this guy gets moved 31 places over that way. He falls outside the scope of the int, so he just gets thrown away. This guy, too, way too far outside the bounds. He gets thrown away. The only guy that actually gets retained is this 1. If you shift the 1 31 places, that ultimately puts him here. And as promised, that effectively now leaves us with a whole bunch of blank spaces. But what the program does is it fills those, it pads those, so to speak, with zeros. So what I've effectively now done is shifted that 1 bit all the way to the left. OK, who cares? Well, the goal now is to print out this original input number 1 bit at a time. So the neat trick that we're about to employ is this. We're going to take our so-called mask, whose currently bit, the only bit that's set in this mask is the last highest most bit, and we're going to AND it with the number up here. If I take my input number here and AND it with this mask, what is that going to have the effect of doing for me? Well, let's simplify, because writing 32 bits is increasingly getting annoying. Let's do this with just 8 bits to simplify. If our number 3 is 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. So that's the number 3. We're going to skip the other 24 zeros. The 1 I had here was 0, 0, 0, 0, 0, 0, 0, 1. And now 1 left shift 31 equals 1, 0, 0, 0, 0, 0, 0, 0. Notice that the next line of code is just to do this. If n ANDed with the mask is true, print a 1. Otherwise, print false. So how is this working? Well, the only thing we're using now is the mask, which are these 8 bits. And so we're ANDing those bits together. And it's bitwise in the sense that you apply the AND to each of the bits individually. So what is 0? What is 0 and 1? OK, 0. What's 0 and 0? OK, 0 and 0. So this is very quickly going to get dull there until we get to 1, 2, 3, 4, 5, 6. What's 1 and 0? 0. 1 and 0? 0. So now the answer is all zeros. So what does that if condition evaluate to? 0, aka false, which means what gets printed. And what did we want to print? 0. OK, now repeat. We won't do all 8 or 32 iterations, but if we repeat, now we left shift the number 1 by not 31 places. And actually, that was a bit of a white lie. We're now doing it 7 places. If I left shift it again, but 1 fewer times because I gets decremented, what does that make my mask look like? 0, 1, 1, 2, 3, 4, 5, 6, right? So this is the second iteration, where we're left shifting 1 only 30 places, or 6 places in this case now. Good. So wouldn't it be 1, 1 when you left shift? But the number we're shifting is 1. Right? So there are no other 1s at play. So now if we AND the number 3 with this mask, what's going to pop out? All zeros yet again. But now let's repeat to the very last iteration of this loop. When I equals 0, 1 left shift 0 just gives us a mask of what? OK, right. So 0, 2, 3, 4, 5, 6, 7. So now this is the last iteration. So we do all this ANDing, and which bits actually now pop out as 1? So 1 and 0 is 0, but 1 and 1 is 1, which means the very last iteration of this loop gives us 1, which is true or false. True, so a 1 gets printed. So I don't think I did this little walkthrough very clearly, but the takeaway is that what this mask allows you to do is test each of the individual bits in the input number n. And if you test it with this mask and you get back a non-zero value, that means one of the bits was in fact set, and so you should print out a 1, signifying that the corresponding bit was set. If you get back all zeros, that means there was nothing there. That means there was nothing there to AND it with. And so it comes back as 0. So the net effect of this program, if we make the program called binary, is that if we ask it for a non-negative integer, please, let's give it the number 3. What it actually outputs is the binary equivalent, just by iterating over each of the bits. If we do something crazier like 65,535, that should hopefully look like that string. Right? All of those bits set to 1. And just to be clear, if we do 65,536, thereby overflowing the capacity of those lowermost bits, we need to now use another bit. We should get back a number that looks now like this. OK, any questions on what I admit was, I think, not the best walkthrough on the chalkboard there? No? All right, well, let's end on that cough. All right, see you Friday.